Here's a topic that much of the rest of this chapter is devoted to, and that is surface integrals, okay, and applications. And a lot of these problems are going to be concerned with fluid flow across surfaces in R cubed, but that's not at first. So if we let z equal g of xy be some surface S, and R be its projection, kind of like its shadow, in the xy plane. In other words, R is sort of like what we would use to get our limits of integration. Okay, well, suppose further that g, the partial derivative of g with respect to x, and the partial derivative of g with respect to y are all continuous at all points in that region R, in the shadow, so to speak, and that there is a function f that's defined at all points on the surface S.
Who knows what evil lurks in the hearts of men? The shadow knows.
Blue Call presents The Shadow, a man of mystery who strikes terror in the very souls of sharpsters, law.
Well, okay, law-abiding citizens like you and me. And so terror has been stricken into my heart by this shadow of the surface S into the xy plane. Okay. Well, if we cut up our shadow region R into small itsy-bitsy rectangles and project those itsy-bitsy rectangles upward to the surface S, it would form a partition of our surface S. And we could pick a point in each sub-region of S, in other words, each one of these rectangular projections onto S, and form the sum, I going from 1 to n, of f of xi, yi, zi, delta si, where delta si is the surface area of the piece, and f of xi, yi, zi is some function, that says the function, but says, I should say some function, evaluated at some point within Si. Notice that our del Si would be approximately equal to, in other words, the area of this Si, approximately equal to 1 plus the partial derivative of g with respect to x squared plus partial derivative of g with respect to y squared, times some delta ai, where ai is the area of the rectangle in R, the shadow area, underneath Si. So if we let the norm of the partition of R be such that it approaches 0, then we define the surface integral of S to be this integral right here, integral of f of x, y, z ds, which is the limit as the norm of the partition approaches 0, I going from 1 to n, of the sum of those function evaluations times the del Si, which is not exactly the area, but it's this constant times the area of that rectangle in the shadow. So, how do you evaluate such a surface integral? Well, theorem 14.10. Sorry, 15.10 should give a clue. So let S be a surface with equation z equals g of xy, and let R be its projection, its shadow, in the xy plane. So if g, the partial derivative of g with respect to x and the partial derivative of g with respect to y are all continuous on that region R, and f is continuous on S, so our function is continuous on that surface S, then the surface integral of f over S is the double integral over region R, so you can pick up your limits of integration from that, f of xyz times the square root of 1 plus g prime of x squared plus g prime of y squared. Okay, well, I should say g prime, I shouldn't say g prime, I should say the partial of g with respect to x here squared and the partial of g with respect to y squared here times dA which I'm not sure if that's going to be dx or dy. And now I don't know if you see, we're going to have a little bit of a problem because we got this f of x, y, z. Well, that seems like, what are we going to do about this z variable, Melvin? Well, if f of x, y, z equals 1, then this is just the formula for surface area of that surface. But it might not be. In other words, it might not be uniformly dense, and we might want to find its, like the density of the lamina with the surface area at a point evaluated might wind up giving us what its mass is, okay? But what we would do to, like, we got a problem with a z is there's going to be a way that we can replace e with some function of, replace z with some function of x and y. So here's an example, one that's pretty easy. Evaluate the surface integral S, where S is the surface 2x minus 2y plus z equals 10. Of course, that's a plane. And x is between 0 and 2, and y is between 0 and 4. So, of course, this is what we want to evaluate. And according to this, we can use a double integral, use our f of x, y, z, and then square root of 1 plus partial of g with respect to x squared. I guess this will be our g, plus partial of g with respect to y squared. So let's have a look. Okay, this g of x, y, if we solved this equation for z, z is 10 minus 2x plus 2y, and so that's what we're going to use for our z. And we can see the partial of this with respect to x is negative 2, and the partial of it with respect to y is positive 2. And so we know our integral can be written as this. This is the x. By the way, what happens is we're going to replace the z with something we know it's equal to, 10 minus 2x plus 2y. So we got x minus 2y, that's from here, plus z, but we're not going to put z in there, we're going to put 10 minus 2x plus 2y in there for z, and then times the square root of 1 plus negative 2 squared plus 2 squared, which is, by the way, that's the square root of 9, so that's where this 3 came from. And 0 to 4 are obvious limits given that y goes from 0 to 4, and x limits similarly obvious, 0 to 2. Simplifying all of this is just 10 minus x dy dx. So you should verify this equals 216 yourself. I just did it with MathCAD. It's, you know, just to save a little time. But there's nothing difficult about any of this integration. First integration, you're going to get an extra y term, but y goes from 0 to 4, so no problem there, I don't think. So what the calculation found is the mass of the section of the plane shown in this picture below, if its density at x, y, z is given by x minus 2y plus z. And here it is. So what we found, you see x going from 0 to 2, y going from 0 to 4, then what we found is the mass of this plane, and that's enough.